Okay, let's get started here. Couple things real quick, then we'll get started. So this is what your first page of your test will look like when we have a test. It'll look exactly like this. I'll have the ID number in there. For the exam number, you're going to put your ID in this square. You're going to put your name in there. You're going to sign this. You're going to read what it says, sign that. You'll have a seat number when we have a test. Okay. Then let me go back in here. I should have this up already. Oh, should have been already up. I thought I had another one up. It's right here. Get out of there. Let me go back. Well, oh, here it is. Sorry. For OWL, go to week 1 in OWL chapter 2 right here. You do not need an instructor code. So if you go through OWL right here, you do not need an instructor key. And you get OWL, they give you a 14-day trial. So you don't even, I don't think you even need a code for 14 days, but eventually it's going to shut you down. So if you just get in right here without a code, realize you're going to need a code within 14 days. So no instructor key, go through right here. Okay, let's go to, let me stop the share on this and start sharing the other. Okay. Let's look at where we left off. Well, I used to do a review, so I'm going to do a review from this. So we're not in here this far yet, so it looks like for review, at least we can look at 13 and 14 quick. So if we are going to put this in scientific notation, we for sure are going to get a negative exponent here because this number is less than 1. And we're going to have to move the decimal point. Looks like 4 places, huh? 4 places for that. And if we are going to take this out of scientific notation into decimal notation, we're going to move this decimal point to the left 3 places, right? Okay, we did just a little bit of scientific notation last time. Anybody that was not here last time? Grab these. Anybody else not here last time? All right, ready to go. One on this side and one on this side. Grab these. There, you got a set of handouts. Okay. Last time I said we talked about this. Who's got an answer for this? Anybody want to volunteer an answer for this? Never mind, somebody volunteer an answer. What do we got? What's the first part of this? Anybody? 1.81? Is it 1.81? No? Well, let's see if I worked in my previous stuff. All right, let's grab this. You got punch this in your calculator from what I circled. Do this. Listen carefully. Take 1.1 times 1.2, hit equals, and then hit your division key 3 times. Go 1.1 times 1.2, enters or equals, hit divide by 9, divide by 9, divide by 9. That is the absolute quickest way to do that. And you should get this number. 0.00181, so on, yes? Okay, times 10 to the, when we multiply these on top, we're gonna add the exponents. So negative 400 plus 708 is gonna be a positive 308. Then this is negative 201. So we're gonna add 201 because we have minus a minus. We're going to do minus 606 and minus 109. So what do we get for that? Is it negative 206? Okay, so we get a negative 206. But we still got to put this in correct scientific notation. Because we cannot leave this as 0.00181. So this is where you got to think this out. If I leave this just the way it is, I would take that decimal and I would move it to the left 206 places, correct? But if I put this in correct scientific notation by moving it to the right 3, my correct answer is 1.81 times 10 to the minus 209. I'd have to move it 209 to the left. So you have to think that out when you get an answer like this, and then you have to put it in correct scientific notation. This is a good video. Get a chance, pop that in. All right, let's go to the next page. So on the next page, we started talking about, I believe, units. And I think we ended with this on the screen right here. Okay. So in the metric system, here's what's slick about the metric system. It works for everything. If this was a meter, if I lined up 1,000 of these, I have a kilometer. If this is a liter, if I have 1,000 of these, I have a kiloliter. If this cat has a mass of a gram, if I have 1,000 of these, I have a kilogram, right? It works for everything. If I take this and divide it up into 1,000 pieces, I have a milligram. If I take this liter and divide it up into 1,000 pieces, I have a milliliter. And if I take a meter stick and divide it up into 1,000 pieces, I have a milliliter, right? It is so slick. It works very, very efficiently. So if you want to go larger or smaller in your unit, since everything's based upon 10, we can simply move the decimal, right? We just simply move the decimal. It's that easy. And if you grew up with the metric system, you would have a chart like this memorized. Your base unit right here is just going to be a single letter. So your base unit, it could be a gram, it could be a liter, it could be seconds. It's just going to be a single letter. You know you have a base unit, a meter. Now, all you have to do is move the decimal the same direction that this chart requires. For example, this is my base unit because it's a single letter, 1 gram. Oops. Let me zoom this out, sorry. 1 gram. If I'm going to kilo, my base to kilo, I need to go to the left, yes? Just on the chart. 10 to the 0, 10 to the third. 10 to the 0 left to 10 to the third. Or I just move my decimal point 3 to the left. The same as what the chart is. So if I move my decimal point 3 to the left, I am going to get 0.001. Number 12, I've got 1 megameter going to my base. Megameter, right here. 10 to the 6th. I need to start at 10 to the 6th. I need to go to the right to get to my base, which is 10 to the 0. I just have to take my decimal point to the right 6 places, right? And if I take my decimal point right here to the right 6 places, I'm going to get a 1, 0, 0, 0, 0, 0, 0. 1 megameter should be 1 million meters. Now here's one where students mess up on a little bit. 1 centimeter. This is my base. I'm starting out right here at 10 to the minus 2. 10 to the minus 2 centi. To get to my base, I've got to go left to 10 to the 0. And you're just looking at the absolute value here. I need to go to the left 2. So my 1 centimeter left 2 is 0.01 meters for 1 centimeter. Millimeters to micrometers. So right up here, I'm going milli to micro. I got to go to the right, 10 to the minus 3 to 10 to the minus 6. I'm going to the right 3. 10 to the minus 3, 10 to the minus 6. I'm going to the right 3. So here I should end up with 1,000. 1 nanosecond. How many seconds? I'm starting here at 10 to the minus 9. I got to go to my base, right? I'm starting at 10 to the minus 9. I got to go to 10 to the 0 this way, 9, right? 9 places to the left. So I have my decimal point right here. And right there's 1 place to the left. So I should have a decimal point with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and a 1. And I'll put a 0 in the front. There should be 8 zeros there. So 1 nanosecond is 0.000001 seconds. Okay. It is a slick system. All we have to do is move the decimal point, right? That's all there is to it. Well, in the United States, we're still using the English system, which England abandoned in 1965, right? So, our first kick at the can for the metric system is the automotive industry switched over to metric to build cars. So in America, everybody bitched and complained because they had to buy metric wrenches. Right? So in the US, we do this. Now I'm going to argue a little bit. I'm going to lobby you a little bit. I can call my father on my cell phone right now. He lives in Florida. He's 83 years old. And I say, Dad, when you were a kid, they told you in elementary school that we're going to switch to the metric system, right? You say, yep. I'm pretty old too. When I went to elementary school, they told me we're going to switch to the metric system. But they didn't even tell you that anymore, either. They didn't say that anymore. So I want you to give me an idea of what we do to our kids. Because in the metric system, all we do is move the decimal point. In America, this is what we do. We take a ruler like this, probably about 3rd grade, and we give the class this ruler. And we say, okay, students. And by 3rd grade, we've beaten all the piss and vinegar out of these students. We brought them to school. Said, you can't shut up. You can't talk at all. We're the things keep chart. One person talks, we're going to nobody go off for recess, right? We take our students and beat all the piss and vinegar out of them. We put this on the screen. Okay, class, what does this measure? And the teacher says, well, the first thing you have to do is figure out how many divisions there are in the inch, right? And the teacher would go, okay, well, how many ticks are there between the inch? And in this case, the answer is how many ticks are there in the inch? 4. This is 1, 2, 3, 4 to get a ½ inch. So there's 8. This is in 8ths, right? Now these little kids are smart. The teacher says there's 8 divisions in the inch. These kids' heads are just a grind. They're always trying to make associations. For example, my kid, that's a basketball game. I said, hey, what number is shooting that free throw? Side by side 1. This was the answer I got back. What number was it? 11, right? Was my son wrong? No. I'm always trying to make associations. Get in the car. Hey, turn the air conditioning on. But turn the air conditioning on. My daughter gets in the car next time. She's cold. She says, turn on the hot conditioning. And then at night, she went and took a shower and she put air conditioner in her hair. So she called it air conditioner. These kids are always trying to make associations. So the only association they can make with 8, how many ounces in a cup? 8 ounces in a cup, right? So these kids are sharp. They're saying, oh, this makes sense. There's 8 ounces in a cup. There's 8 divisions in the inch. You know what we do to those kids next year? Put this ruler on the screen, right? That's what we do to them next year. We put that up there. The teacher says, okay, class, how many divisions are there in an inch? So these little 3rd graders, 4th graders said, sure, this teacher must be stupid. Last year's teacher said there's 8 divisions in an inch. And adults aren't supposed to lie, right? Then next year, the teacher has to say, well, we lied to you last year. There's really 16 divisions in the inch. These students are trying to make associations, right? The hand should shoot up. Should say, does that mean this year there's 16 ounces in a cup? Right? Then we really blow their mind. We keep going. And then we tell them how many inches are in a yard. How many inches are in a yard? 36. Well, what's the association? They're trying to crank something out of their head, right? They're so sharp. And the only thing that's close is how many ounces in a quart? 32. Nothing. There's no association in this system. This system makes no sense. It's a crap show. It's an absolute crap show. How many feet in a mile? 5,280. Then we give them a problem like this. We say, okay, students, before you go for recess, I want you to figure this problem out. Your parents measured 2 walls, and this one was 3 feet 8 inches, and this side was 6 feet 6 inches. What's the total of that distance? Well, the student goes, okay, I can do that. 3 feet 8 inches and 6 feet 6 inches. Let's see, 14. So that's 4 inches carried to 1. That's got to be 10 feet 4 inches, teacher. You said, no, that's not right. Why isn't it right? The student was smart. Because the student was very smart. Let me move this up. Sorry. That student goes 8, 6 is 14, right? That student assumed there's 10 inches in a foot, right? Because that makes sense. Carried the 1. 10 feet 4 inches, completely wrong. The student's smart enough to think, who the heck? Why would they put 10 inches in a foot? Who the heck would want to stick 12 in there? To confuse us. You know what the teacher says next? That's completely wrong. Convert everything to inches. So 36 inches and 72 inches. So we got 44 inches here, right? We got 44 inches here, 72. We got 78 inches here, 12, 11, 122 inches. Right. Yeah, that's right. 122 inches. Can I go off for recess? I just want to go for recess. Nope. Convert that back to feet and inches, right? That's the crap we're teaching our kids. It makes no sense in what we're doing. So, you become a politician, get us away from this crap. This does not make any sense. It makes no sense at all. Now, and then you're going to have your old grandpa's going to say, we don't need to switch to the metric system. I got a reply for that. Grandpa, what car do you drive? What car you got in your garage? Oh, I got a 2020. I don't have a car. I got a 2024 F-150 pickup. So, Grandpa, did you ever drive a 1950 car? Well, yeah, of course I did. Why don't you drive one today? You don't need to switch. You don't need to get power, right? That's what you do. Those old people. You just tell them. Drive the car you used to. If it was good enough back then, it's good enough today. Okay. It is a crap show what we're teaching our kids. But that's what we got to deal with then. Look at this. All right, look at how great a system we have here. So we have to convert differently because we can't just move the decimal. And to do that conversion, we should be canceling units. So here's an example. And it works like this. If I come over here, and let me show you this. If this is, don't write this down at all. If this is 2 feet and this is 4 feet, how many square feet? 8 square feet, right? You have 8 square feet. My point is this. It's feet times feet. You're also multiplying, you're multiplying the numbers, but you're also multiplying the units, right? So we would write this down as 8 feet squared. Well, what if I said this side is X and it's 8 feet squared? What is X? Well, you could go like this, and you could go 8 feet divided by 4 feet, right? My point is this. If you have the same unit in the numerator and denominator, you can cancel that out. So in the English system, we have to convert units and eliminate units when you have the same one in the numerator and denominator. Does that sound like something you've done before, correct? So all you have to do is put a true mathematical statement. You'll see me do these as H's. I call them conversion H's. So if we have 3/16 of an inch and we want to figure out that in millimeters, I can go 1 inch. My inches cross out here, and my centimeters cross out here, and I'm left with millimeters, right? You just have to put true mathematical statements in here. So a 13/16 wrench would need a 21 millimeter. Then I give students this problem and I say, we're going to convert 1.2 decades to seconds. Now, please, please, please don't try to look these up and do it in one step. Go with what you know. Could you do this in one step if you knew how many seconds are in a decade? Absolutely. But here's my cancellation of units. Again, all these that you see here are just true mathematical relationships. I can eliminate decades, I can eliminate years, I can eliminate days, hours, minutes, and I'm left with seconds. 90+% of you have done this. Okay. And so let's do this one down here, 16. So again, the grade English system. If we have 135 ounces, I do this. I call it a conversion H. How many ounces in a pound? 16. And I know no matter what, I'm going to put something with ounces down here. Because I started out with ounces. And this is the numerator if you want to put a line like this. So yes, 16 ounces, 1 pound. We know that's all there is to it. In number 17, we have 1.75 miles to yards. So 1.75 miles. Now we can do this in one step or two. If you know how many yards are in a mile, that'll work. But it doesn't matter how many steps you take. Most of you probably do not have that number off the top of your head. You know that 1 mile is 5,280 feet, right? Most of you know that. And then we still got to get the yards, so we're just going to add one more step. Then that is going to be 3 feet in 1 yard. And you can punch that in your calculator. All right, let's go to the next page. The next page involves area and volume. And it goes between the units, but let me do. We'll look at this example here first. So I've got this labeled converting between the systems. This is English. And this metric. These are a couple of them you should memorize. 1 inch, 2.54 centimeters. By the way, this is exact. This is really, really rare. This is 1.0000 inches. This is exact equals 2.540000. Keep going. Centimeters. That one is spot on. That is the only one I can think of that is absolutely spot on. The rest are rounded somewhere. If we're converting 1.5 tons to grams, we're going to eliminate tons because we're going 1 ton is 2,000 pounds. And then pounds to grams. This is English to metric, right? English to metric. Okay. Now let's talk about area and volume. First of all, in the metric system, if I have something that looks like this, let's say I've got 1.5 cubic meters to, let's say, cubic millimeters. I can still use my same chart, my exact same chart. And that chart, by the way, is on top of your green sheet. Now, here's how this would work. In the metric system, this meters cubed is my base, right? This is my base. I want to go to millimeters. Just forget the threes. If I want to go 1.5 meters to millimeters, I need to go to the right. How many places? 3, right? I need to go to the right 3 places. Since I have cubic units, I need to go to the right 3 places 3 times. If I had square units, I would go to the right 3 places twice. That's pretty easy to do, right? There's nothing to it. So I would have to take this decimal point right here to the right 9 places. So 1.5 cubic meters would be the same as 1.5. That's 1, 2, 3, 4, 5, 6, 7, 8 cubic millimeters. Again, the metric system, you just move the decimal point. Well, here comes that sweet English system. Here we go. If I have 1 square foot, be careful now. Be careful now. How many square feet? It's not 2, it's 1. I love you. That's 2. Well, no, it's 1. It's 1 square foot. Yes? Right. Now, if I change the foot to 12 inches, how many square inches? 144, right? 144. In fact, I could go 12 this way. I didn't count them, so I can go 12 this way. I'd have 144 little squares, right? So we know that 1 foot squared is equal to 144 square inches. But I'm not going to do it that way. I'm going to do it like this. And if we have square units, we simply do this. It's the same thing. 12 squared is 144, right? If we have cubic inches, check this out. We'd have to go this direction then. And then in this sweet English system, 1 cubic foot then can do that. Right? This 12 cubed is 1728. Why try to memorize 1728? We're going to multiply or divide by 12 3 times. Here's the example. Here's my example. I'm going to take 0.00250 square feet to square centimeters. 1 foot is 12 inches. But I'm going to square it because I'm starting with square units. Then 1 inch, 2.54 centimeters, and I'm going to square that. So in my calculator, it is this. .0025 times 12 times 12 times 2.54 times 2.54. That is the slickest, easiest way to do it. All of my units cancel out. If I have cubic units, I'm going to do the mathematical operation 3 times. So I have 1.50 times 10 to the 8th cubic millimeters. I'm going to cubic feet. (10 millimeters in 1 centimeter). Well, I'm going to divide by 10 3 times. 2.54 centimeters in 1 inch. Cube these. I'm going to divide by 2.54 3 times. 12 inches in 1 foot. I'm going to divide by 12 3 times. This is what I'm going to do in my calculator. So that's how you handle square and cubic units. Just do the mathematical operation 3 times for cubic units, 2 times for square units. All right, try to do 18, 19, 20 here. I'll let you do that. Now, I want to talk about, we have to talk about Sig Figs, of course. First of all, let's talk about a little bit of accuracy and precision. This, you're accurate because you're hitting the target and you are precise. Now, there's 2 ways to look at precision. One of them is this. If I want to measure out, this is a 10 milliliter graduated cylinder. See if I get this right there. We can see the 10 right there. If I want to measure out 10 milliliters with this versus 10 milliliters with this beaker, which one's going to be more precise? Which one's going to give me more digits? This is, right? This is going to give me more digits. Now, precision here is how close are you in your measurements? So this could happen in lab, especially the CO2 lab. You do the lab 3 times. Whatever you did a great job. All 3 results are very, very close. You just didn't get the right answer. Well, it'd be an example of that. You went to the same balance and never teared it down to 0. There was a number on there. You did it 3 times, went to the same balance. When you come back, you had the wrong number 3 times, correct? That'd be an example of where you could do very precise work in lab, but never be accurate. And of course, this is a mess here. Now, let's talk about significant figures and why you have to do it. I'm going to give you 3 quick examples. Basically, we do Sig Figs, so you're not a liar. So, example number 1. You're broke, you know that Wisconsin's going to legalize marijuana and you're going to get a jump on it. So you got a big backyard, you take a shovel to your backyard, you start digging, and whoop, oh, you hit something. You dig it all up and you say, whoa, this looks like a dinosaur bone. Huh, I'm just going to sell this thing. Huh. So you list it on eBay as a Wisconsin dinosaur bone and you start the bidding out at $10,000. Get a message back right away. Well, first of all, when you back up, you need to send that thing in for carbon dating. I got ahead of myself. You send it into carbon dating, comes back, it's 3.5 million years old. 3.5 million years old. That'd be 3.5 million years old. You list it on eBay. Somebody messages you back right away and says, huh, what are you doing? There's no dinosaurs in the state of Wisconsin. That thing is worth nothing. Oh, so you're deflated. So you put it above your fireplace now. 5 years later, a relative comes over. Says, oh, looks like a dinosaur bone up there. How old is it? Well, that's easy. It's 3,500,000 and 5 years old. Is that true? No, because this number right here is only within 100,000 years, right? You can't 5 years later say it's 3,500,000 and 5 years old. You can't do that. Here's another example. 3 measurements for this triangle. 2.1, then you get a more accurate ruler and you do this as 11.62, and then you even get a more accurate ruler and you do this as 9.416. Grab your calculator. What's the perimeter of this? Grab your calculator. What's the perimeter of this? Because your calculator doesn't lie, and your calculator is going to give you 6, 3, 11. Am I doing this right? 3, 4, 13, 23.136. Okay. 23.136. If you look the answer up in the back of the book, it is not going to be 23.136, correct? My question to you is this. What number is right here? No, what number is right there? What number is right here and what number is right here?
0.
You have no idea what the number is. What number did your calculator assume? 0. Did you measure out to 3 decimal places here and here? Would you agree that if you had this third ruler for all 3 measurements, there would be a number here and it could be a 0 through a 9? And there would be a number here and it could be a 0 through a 9? So you'd be a lying sack of you know what if you wrote down a 6. You have no idea there's a 6. In the same way here, this could be a 0 through a 9. You can't write that number down either. You didn't have an accurate enough measuring device. So what you would do is you would look at this as a 3, you would leave this a 1, the answer would be 23.1. Okay, that makes sense because you can't lie, right? Otherwise you'd be lying. Here's my third example. Take this. Switch the screen. I think I got the right color on. We are going to read the right side of this. I'm going to cheat maybe a little bit. How many milliliters of water? Right scale. 550 is in the middle. Can we say 530? I don't know. 530. right? 530 milliliters. 530 milliliters. Got the right, let's see. 530, let's see if I can get this to go. Turn this around. I'm not going to be able to hold this very well. You get the idea. Let me put this down here. So the first one was 530 milliliters, and we just estimated the tens place, right? We have no idea what the ones place. Now this is about 2.20 milliliters. So if I do this, if I dump this in here, are you now going to tell me inside that big beaker is 532.20 milliliters? There's no way, right? There is no way you could write this down. There's three pretty good examples of Sig Figs and why we use them. Basically, it's so you're not a liar. Now, let me make one more point. If you have me for lab, this is going to be what I'm going to be saying today. If you have this measuring device here, and you're doing the length, width, and height of an object, and I get results like this, well, first of all, you got to be on the metric scale. Let me see if I can zoom in on this. Can we call that right there 5.95? No. No, am I off that much? We can't? Would that be 5.95 centimeters? All right, halfway in between there. Yeah, isn't that 5.95? 5.90 there. Halfway in between, 5.95.
Not precise, but accurate.
But we can estimate that 5, yes? What would this reading right there be? 6.00. If this is 5.95, this is 6.00. My point is this: if you're using that ruler, I cannot get lab results like this. Length 4 centimeters. My width is 2.1 centimeters, and my height is 1.63 centimeters. I'll get numbers like this. And I'll write in, did you change rulers? If you are using the same measuring device, the precision, the decimal places need to be exactly the same. Does that make sense? So when you do lab next week, make sure this is what you're dealing with if you're using the same device. Okay. Next time we'll try to finish everything up on Friday. If you have not punched all of these in, do this. Show up next time with the calculator, all these digits filled in. We got to do the rules of Sig Figs.